from UCS. Thank you. Yeah, we're very happy to have Nathaniel from UCSB. Nathaniel did his PhD from Stanford and then spent a few years at the IAS and Rutgers, and then he had moved to UCSB with his current position. He's worked on a bunch of different things. So feel free to chat with him after the talk perhaps, but today he's gonna tell us about broken hierarchical symmetries in particle physics.
All right, thanks, Shelby. Thanks for the generous introduction. Thanks everyone for coming and for having me. It's always, of course, a pleasure to be here. So indeed, I'm excited to talk to you today about broken higher-form symmetries in particle physics. Higher-form symmetries, generalized symmetries, broadly speaking, have of course been a very hot topic over the last decade. But I think the penetration into particle physics in ways that tell us things that are genuinely new has been a little bit slower. And so part of the motivation today is just to try to push in some directions that seem promising. And so this is based in part on work with this amazing graduate student who happens to be here at NYU, Marius. And so you, of course, may have heard aspects of this work, so I will be a little bit more concise with some of the details, as well as some work in progress with Dan Sahayek, who is one of my students at UCSB. Yes, I should say, since this meeting is being recorded, I will be guarded with most of my comments. If you'd like the unguarded version of those comments, feel free to ask me afterwards when the recording is turned off. I think the question about how generalized symmetries interface with things that we already do in particle physics is a complicated one, and so I want to make sure I treat it carefully. Just so I orient with the audience, normally when I give this talk to a particle physics audience, there's varying degrees of background familiarity with generalized symmetries, so higher form symmetries, non-invertible symmetries, higher group symmetries. How many people feel like they have a good working knowledge of generalized symmetries? Okay, how many people feel like they don't have a good working knowledge of generalized symmetries? Okay, good. So this talk is not going to assume much background knowledge about generalized symmetries. I will try to introduce, from a particle physicist perspective, some of the things that are important. So hopefully it keeps everyone on board. For those of you who already know these things very well, of course, please don't underestimate the pleasant, warm feeling of hearing things you already know. And also, please forgive me slight imprecisions that I'll conduct in the interest of time. Okay. Oh, this is being recorded, so. All right. Oh, got to click my double jeopardy. All right. Okay, so my background picture. This is part of my interest in generalized symmetries. Is I think just part of a general perspective that I think many of us in the field have had over the last decade, which is that we, for a very long time in particle theory, had what we thought was a very clear idea of what physics lay beyond the standard model. And we developed that picture very completely. And then we turned on the LHC and a number of other large-scale experiments. And we learned that that picture was not realized in nature. And so over the last decade, I think what many of us have done is recognize that we were looking, in some sense, under a lamppost. And we've now spent the last decade sort of looking and recognizing that this is a vast universe of possibilities, many of which are cosmological and astrophysical in nature. And the spirit of the talk today is that, not only, of course, are there many interesting other directions for physics beyond the standard model in terms of experiment that we're exploring over the last decade, but also that there are interesting directions in theory. And so the question is, are there interesting, since we're in sort of a golden age of quantum field theory, are there interesting theoretical developments that we can bring to bear on the problems of particle physics? And as I hope I'll convince you through my talk, bringing some of those tools to bear, especially in the framework of generalized symmetries, I think is promising. And also it turns out that some of the places then that you're, again, compelled to look for experimental signatures is also astrophysical and cosmological. So this talk is not going to be a lot about astrophysical and cosmological observables, but I do want to touch on some of that as motivation for future directions. Okay, sorry, back and forwards is upside down. All right, so this talk has three parts. Part one, for those of you who haven't thought much about generalized symmetries, I do just want to give a concise introduction to some of the salient ideas that will then play a role in later parts of the talk. Part two is going to be about the work that I've done with Marius, which I think is a very useful demonstration of the power of generalized symmetries to organize information for physics beyond the standard model. And part three actually is a trip back to the 1980s, where thinking about generalized symmetries, I think, teaches us some things that were missed back then that possibly have some interesting phenomenological consequences. Okay, so part one, so what are, from our perspective, how should we think about generalized symmetries? Well, the first thing I want you to do is think about a familiar way of describing ordinary symmetries in a new way. So of course, for ordinary symmetries, if you have an ordinary internal symmetry of your theory, you have some, if it's a continuous symmetry, you have a conserved current. You take that current, you take the time component of it, you integrate it over some spatial slice at a fixed time. You call that a unitary that implements translations or transformations by the symmetry on your fields. And that's something that we know and love how to do. So the only thing that I'm going to ask you, the one step I want you to take forward from that picture is just to imagine doing the same thing, except now instead of integrating the time component of your current over a slice of space, instead just doing that same thing over some general codimension 1 manifold of your space-time. And so you're integrating the normal component of your conserved symmetry current over that d-1 dimensional manifold. And this thing you maybe shouldn't necessarily call a unitary operator, so we'll call it a symmetry defect operator. And it turns out these have lots of nice properties for global symmetries that recapitulate the properties of the global symmetry itself. So among other things, these symmetry defect operators obey the group multiplication law. So if I have two symmetry defect operators, each one corresponding to a different group element, I define them on the same surface, and I bring them together, that corresponds to the symmetry defect operator that I would have gotten by taking the group product of the two elements. So that's good. They are topological, which is the sense in which, as long as you're not enclosing any interesting objects, the surface on which you define these symmetry defect operators, you're insensitive to small deformations of it. And the way that you normally check that is you say, well, let me define a symmetry defect operator on some surface, and let me define its inverse, to take the inverse group element on some slightly different surface. And if these surfaces, if these symmetry defect operators are topological, this should still act as the inverse, even though it's on a slightly deformed surface. And you can see that this is in fact true, because if you take the product of these things with this definition, it turns out that this just gives you something, the exponential of now the divergence of your current in the volume bounded by the two surfaces. And of course, if your current is conserved, this divergence vanishes and you get the identity. And so you learn that the symmetry defect operator, the inverse element defined on a slightly deformed surface, acts just like you would expect the inverse to on the same surface. So you say that the SDOs are topological. And then the final thing that these do is just like you would have done with your ordinary unitary transformation, you can think of these as inducing symmetry transformations on charged operators. So in some sense, if you take a symmetry defect operator and a charged operator localized at a space-time point, and you in some sense pull the symmetry defect operator past this charged operator, for example, by taking it to a surface that crosses over the location of the charged operator, then this implements the appropriate transformation on the charged operator in the suitable representation. Okay.
You are Euclidean.
Yes, this is yes. Okay, so the basic idea, so this is all just new ways of talking about old things. But once you have this idea in mind, in some sense, the set of symmetry defect operators and their relations recapitulate all of the properties of your symmetries, you can now say, well, are there new symmetries that I can attempt to identify by defining appropriate sets of symmetry defect operators? And the basic observation in this now very famous paper by Gaeta, Kapustin, Seiberg, and Willett is you can take the natural generalization instead of having symmetries that act on charged operators defined at points. You could have them, the charged objects be extended objects. They could be line operators or branes of various dimensions. And there could be antisymmetric tensor currents that are conserved under which these objects are charged. And we can appropriately define the notion of symmetry transformations by defining corresponding symmetry defect operators. Again, once we have the currents, we can define symmetry defect operators in the analogous way. And these now give us a well-defined notion of higher form symmetries where the charged objects are higher dimensional. And in particular, if I have a p-dimensional charged object, so for example, the simplest ordinary symmetries would then be zero form of zero-dimensional charged objects. The simplest generalization to higher forms would be a one-dimensional charged object. The conserved currents are p+1 index objects. And the codimension of the symmetry defect operators goes up as the dimension of the charged objects goes up. That is to say, the dimension of the symmetry defect operators goes down in such a way that there's always a well-defined linking between the charged objects and the symmetry defect operators in a fixed dimension. I should say at this point, this is largely irrelevant for the talk, but in case the notation becomes confusing, once you, of course, are dealing with high index objects, differential forms are basically obligatory, and it's conventional in the generalized symmetries community to take, since the currents themselves that are conserved as forms would be co-closed, it's conventional to define the symmetry defect operators via the closed dual d minus p minus 1 form. And so this is the notion of defining a symmetry defect operator for now a p-form symmetry. Okay, this isn't going to be important for what follows, but the notation, just to avoid confusion with the notation. One of the important physical implications, especially for a particle physicist, you can ask, what is the structure of these symmetries? And a very important initial observation you can make is that these symmetries are necessary abelian once p is greater than 0. A simple way to see that, just imagine you're living in 3 dimensions. You have a one-form symmetry, so the charge objects are, say, lines, and the symmetry defect operators are also one-dimensional. And in this picture, I have a charged object which is enclosed by 2 symmetry defect operators corresponding to different group elements. If I pulled them both past the line operator, that would introduce a transformation first by G1, then by G2. But since these are topological, of course, I can deform them by moving the inner one down and out and back up. And now, of course, if I pull them across, I would implement G2 followed by G1. Since these have to be the same thing, that tells you the symmetries are abelian. So as a particle physicist, the initial reaction is usually one of disappointment because we're accustomed to non-abelian symmetries being the most interesting, but hopefully I'll persuade you today that there's still a lot interesting, even restricted to abelian symmetries. Okay, so it turns out, of course, these, although, in some sense, these are exotic sounding symmetries, they've been with us for our entire lives in high energy physics. This is both a blessing and a curse. It's a blessing because the language of generalized symmetries allows us to recognize global symmetries in places where we may not have recognized them before. The curse is that, generations of physicists are all very smart people. They have found ways to understand and describe the physics of the systems that we study. And so many of the phenomena that I think are organized in the language of generalized symmetries, we already have other ways of understanding and talking about. So the real challenge, I think, if you're trying to find lessons that you can learn about particle physics using the language of generalized symmetries, the challenge is to recognize what things we already knew versus what things we can learn with this new perspective that might be original insights. Okay. But some examples of the generalized symmetries that live everywhere around us just in 4 dimensions. The canonical example, which I'll come back to in various guises for the rest of the talk, is if you just think about electrodynamics with no charge matter, there's in some sense 2 one-form symmetries. The first one is what you might call the electric one-form symmetry, where the 2-index conserved current is just the field strength tensor. So, of course, in the absence of charged matter, this symmetry current is conserved just by the equations of motion. Now, as you know, of course, in a field theory, you can define an infinite set of conserved currents. The question is there anything interesting charged under them? And in this case, there is. The objects that are charged under this electric one-form symmetry are just the Wilson lines of the theory, which you could think of as the world lines of charged particles carrying charges Q. There is, of course, also a second one-form symmetry of Maxwell theory, which is what you might call the magnetic one-form symmetry. This is just what you get just by taking the dual field strength tensor. And in the absence of monopoles, this is conserved by the Bianchi identity. And unsurprisingly, by electromagnetic duality, the charged objects in this case are the 't Hooft lines or the world lines of magnetic monopoles. Okay, so these examples we'll be coming back to in various guises later in the talk. 2 other things, of course, that are worth mentioning. One is that periodic scalars like the axion, of course, they have the ordinary zero-form shift symmetry that we're accustomed to as a version of a Goldstone boson. But they also have what you might call a 2-form symmetry, which is the symmetry current now is a 3-index object, and you just get by taking the Levi-Civita tensor contracting with 1 spacetime derivative. And this is trivially conserved just because the anti-symmetry of the Levi-Civita tensor guarantees that another derivative will vanish. But of course, what's interesting now for a periodic scalar is that there are objects charged in this 2-form symmetry, and they are the world sheets of axion strings. Right? So it is productive, especially for axions and periodic scalars, to think about there also being a 2-form symmetry in addition to the 0-form shift symmetry that we're familiar with. And then finally, and this is probably the OG higher form symmetry, of course, we've known for a long time that gauge theories, Yang-Mills theories, have a center symmetry that is an interesting diagnostic of confinement. It turns out nowadays we recognize the center symmetry is also a form of a 1-form symmetry. It's not a continuous symmetry, so there's no continuous symmetry current, but it has all of the properties that you expect of a discrete generalization of higher form symmetry. And the charged objects here are the Wilson loops in different representations of Yang-Mills. Okay, so these symmetries are all around us. They're in all the theories that we know and love. They're in the standard model. And so the real question is, do they, just thinking about these symmetries, tell us anything that we didn't already know? Now,
here,
yeah,
when you wrote those, you reverted to the language of currents instead of forms.
Yes, and not just because thinking in 4 dimensions and trying to make contact with particle physics, I think it is, it is natural, right, to just think about the 2 and 3 index tensor objects. But in an abstract language of differential forms, of course, we could say the same thing. But something I think that's important if you want to ask, how is this useful for particle physics? As I like to say, particle physics is not the art of exact symmetries. Particle physics is the art of broken symmetries. In some sense, the figuring out what the correct approximate selection rules are from approximate symmetries is kind of a lot of the substance of life as a particle physicist. And so the questions we should start asking as we try to put this to work for particle physics are, what does spontaneous and explicit breaking of these higher form symmetries look like? Because that's where we might expect to learn something new about theories that we already know. A few things to keep in mind. One is that these higher form symmetries can be spontaneously broken, just like zero form symmetries. And they give rise to, if it's a p-form symmetry, it generalizes in the way you might naively guess, namely spontaneously broken p-form symmetry gives rise to p-form Goldstone bosons. Now, to figure out a criterion for spontaneous symmetry breaking, it helps to make an analogy with spontaneous breaking of a zero form symmetry. So for a zero form symmetry, one way you might characterize spontaneous breaking is you'd say, well, if I have a charged operator, I can consider the charged operator localized at 2 different points, take that at large separation, and what I see is that this should factorize into the individual non-zero expectation values of the operator at each point, and we would say that's a criterion for spontaneous symmetry breaking. But the slogan might be, this only depends on the points on which the operators themselves live and not on their separation. And that slogan gives you an idea about how to define the corresponding criteria for spontaneous symmetry breaking for higher form symmetries. So in this case now, the charged operators, of course, are extended. They're p-dimensional objects for p-form symmetry. And you could say that the corresponding criterion should be that if you have a charged operator that's defined on some surface, if it acquires an expectation value that only depends on that surface and not, for example, on the volume that it encloses, that would be the corresponding generalized criteria for spontaneous symmetry breaking. And so the idea would be, for example, if you have a Wilson line of some charge defined on some surface, if it has some expectation value, which is in an appropriately scaled limit finite, then this is the matching criteria for spontaneous breaking of the higher form symmetry. And again, just to bring it back to these very concrete examples in 4 dimensions, as you know, when you're taking your first year QFT, and either in Peskin and Schroeder or Mark Cernicki's textbook, you compute some expectation value of some Wilson loops in electromagnetism, and you observe that they have perimeter law scaling in the Coulomb phase, which is precisely scaling that only depends on the surface on which the Wilson lines are defined and not on the area they enclose. And so you would say that this electric one-form symmetry is spontaneously broken in the Coulomb phase of maximal theory. And so a conclusion you would draw from that is that the photon, for example, is the Goldstone boson of the spontaneously broken one-form symmetry. This statement was made in various guises a long time ago, but it's organized nicely in the language of generalized symmetries. Now, I should say, before you get too excited, if you go up in all the different generalized symmetries and you ask, can I explain the masslessness of fields in a new way? The answer is no. So it's only spontaneous breaking of zero form symmetries explain the lightness of scalars. Spontaneous breaking of all of the other higher form symmetries, there's always a mismatch between the number of degrees of freedom in a massless and a massive field. And so you could also explain their lightness, not with respect to spontaneously broken symmetries, but with respect to counting of degrees of freedom. So as far as I know, this insight doesn't tell you, new ways of protecting fields from spontaneous symmetry breaking, but it's a useful way to talk about it.
And this also works without charge matter while the photon is massless, even.
Yes, although the photon enjoys double protection, so it's also the Goldstone of the magnetic one-form symmetry, and so that is a sense in which you can understand the massless of the photon even if there is charge matter and the symmetry is explicitly broken.
But I thought perimeter was perimeter law was for the Higgs phase. So
Well,
yeah,
so certainly I have perimeter scaling in the Coulomb phase, right? Appropriately defined. So this is absolutely true. And of course, for at strong coupling, either in the abelian theory and the lattice or in the non-abelian theory, then we have area law scaling. Okay, what about explicit higher form symmetry breaking, since you mentioned it? And this is, again, becoming more interesting to us because it turns out that most generalized symmetries that are relevant for particle physics, they are not good symmetries in the ultraviolet. They typically become symmetries in the infrared. And so it's worth understanding the extent to which they're emergent symmetries and how that happens. So the general slogan is that charged matter, which is to say not things charged under the higher form symmetry, which are extended objects, but rather things charged under the zero form symmetries on top of which the higher form symmetries are typically built, they explicitly break the higher form symmetries. And again, the best concrete example to keep in mind is just to think about this electric one-form symmetry of Maxwell electrodynamics. If I have charged matter, then that explicitly breaks the one-form symmetry. There's two intuitive ways of saying that. One is that clearly now the equation of motion has a matter current on the right-hand side. So the current is no longer conserved. And if the current is no longer conserved, the symmetry defect operator is no longer topological, so it no longer is a faithful representation of symmetry. Another way to say it is, if I have dynamical charged matter, of course, if I have a Wilson line, I can now split it by pair producing a charged particle and its antiparticle. And now that Wilson lines become endable, then rather than having symmetry defect operators pulled across the charged objects to introduce a symmetry transformation, I can simply unlink them, so they're no longer inducing symmetry, well-defined symmetry transformations. Okay, so this sort of charged matter, in this example, it's things charged under the U1 gauge symmetry, not things charged under the one-form symmetry. If they're dynamical in theory, they break the symmetry explicitly. But you can ask what happens, of course, if these charged particles have mass, then below the mass of the particles, if I'm just thinking about the zero charge sector of the low energy theory, I should imagine that the higher form symmetry is an emergent symmetry. And it's more interesting than emergent zero form symmetries, because of course we know emergent zero form symmetries, typically there can be irrelevant operators that break them, and that has very strong consequences in the infrared. For example, zero form symmetry that is explicitly broken in the UV, that explicit breaking the UV can still do things like gap Goldstone bosons. But if higher form symmetries are emergent in infrared, even if they're explicitly broken in the UV, of course, they're sort of much better symmetries than emergent zero form symmetries. There's various ways to see this. One is that below the scale of charged matter, these higher form symmetries become exact in the local Lagrangian density at lower scales. A good example, again, to keep in mind is if I just had electrodynamics with some massive charged particle, below the mass of the charged particle, I could integrate it out and get an Euler-Heisenberg Lagrangian. And though you might think in the Euler-Heisenberg Lagrangian, the equations of motion would tell you that my one-form symmetry current is no longer conserved, all the terms on the right-hand side have the form of the divergence of something. And so in fact, I can just define an improved current, which is conserved. So in some sense, in the local Lagrangian density below the scale of the charged particles, the one-form symmetry becomes exact. Yeah.
I remember something about this paper confused me when it first came out, which is that unlike sort of every other phenomenon we observe in effective field theory, this is describing a symmetry that is true in the EFT at all orders in perturbation theory, all orders in the derivative expansion, and yet is not true in the UV completion. And it seems to like break decoupling and
and the answer is because there's various ways to say it. One is, of course, since there are no point objects charged under the higher form symmetry, where you would see that there's effects in infrared is if you constructed an effective action for the Wilson lines. And what you would see, so you can actually do this, it's particularly nice to do on the lattice. It's a little bit more complicated to do in the continuum. But on the lattice, what you can do, of course, is you can integrate out charged matter in the hopping parameter expansion. And what you can see is then if you want to describe the expectation value of Wilson loops in the infrared, so now you have you need an effective description of extended objects. And you find that it is given by the sum over Wilson loops, each of which is weighted with e to the minus mass of the charged particle times size of the loop. And so that there, in some sense, those are the Wilson coefficients that encode the explicit jumping, but you only see them in the effective description for the extended objects, not for the local Lagrangian density. So that's where the breaking manifests in the infrared, but unsurprisingly, it doesn't show up in the local Lagrangian density because none of these operators are charged under the higher form symmetry. So I say nearly exact, and indeed you've anticipated the caveat. The breaking, you can track the breaking if you construct the effective theory of the non-local objects in the infrared. Okay. But these symmetries, from the local perspective, these symmetries are much better than emergent zero form symmetries. Okay, the final, of course, way that you could break a symmetry that's very interesting, and I do want to dwell on this a minute because it'll play an interesting role in the two examples I'll give you later in the talk. Of course, we can also break global symmetries with anomalies, and there's sort of, morally speaking, two different types of anomalies we might be interested in. We are, of course, interested in true anomalies, ABJ anomalies. We have a global symmetry that suffers from an ABJ anomaly, and we'll see that in this case, there's an interesting class of generalized symmetries called non-invertible symmetries that arise in the presence of an ABJ anomaly. You can also instead consider a sort of fictitious anomaly, which is in a theory where even if you don't have any gauge degrees of freedom, if you only have global symmetries, you can imagine that some of these global symmetries were gauge symmetries with very small gauge couplings. And it could be that if you gauge the symmetries, there would be ABJ anomalies. And the theory has to obey consistency conditions compatible with the possibility that the theory could just be very weakly gauged. And so, of course, those are 't Hooft anomalies, and 't Hooft, people that use lots of, they are very powerful in, for example, describing the infrared phases of gauge theories. And in the case where we have a higher form symmetry in the presence of 't Hooft anomalies, we actually get an interesting mixing between symmetries of different degree, which are characterized by what we call higher group symmetries. And it turns out these have very interesting consequences for phenomenology. So I want to spend a little bit more time on them just at the level that we'll need, because this is maybe a place where we can stand to learn new things about particle physics from the language of generalized symmetries. So let me start with the 't Hooft anomalies, and then I'll briefly say something about the ABJ anomalies. Both of these, of course, are talks on their own, so I'll be very concise, but try to give you the interesting things. Okay, so a higher group symmetry. So again, here the idea is you have a higher form symmetry, but there's also some sort of 't Hooft anomaly at play. So some anomaly between just global symmetries that would be a genuine anomaly if the symmetries were gauged. And so to see why this is interesting, consider a genuine U1 gauge theory in 4 dimensions and 4 fermions charged in it, which transform under an ordinary zero form flavor symmetry. So U1G denotes the gauge symmetry, U1F denotes the flavor symmetry. Here's the 4 fields and their charge assignments. So, but these charge assignments, this theory is free of ABJ anomalies. So there's no U1F, U1 gauge squared anomaly. But there is what you might call a 't Hooft anomaly, and I'm putting it in scare quotes because it's neither a true 't Hooft anomaly nor a true ABJ anomaly. It has 1 insertion of a gauge symmetry current and 2 insertions of the flavor current. And this has a non-zero anomaly coefficient. Okay. The theory, as we defined, it also has a magnetic one-form symmetry because just by construction, by assumption, there's no monopoles. And the fact that there's a 't Hooft anomaly involving the ordinary symmetries has a really interesting consequence. So now, as we often do when we're analyzing the consistency conditions implied by 't Hooft anomalies, we say, let's imagine turning on background gauge fields and coupling them to the ordinary symmetries. We can couple them both to the zero form global symmetry, but we can also couple them to the magnetic one form symmetry. And now, of course, once we've turned on these background gauge fields, we can imagine if we did a global symmetry transformation, the parts that participate in the 't Hooft anomaly will have an anomalous variation, whereas any non-anomalous global symmetries will be well defined. And so we find that that's true here. The magnetic one-form symmetry is just a good symmetry on its own. So it has a conserved current, and the theory is invariant under transformations of its background gauge fields. The U1 flavor symmetry, because it participates in the 't Hooft anomaly, it has an anomalous variation where one of the field strengths that appear in the variation is the actual gauge field strength, and the other one is the background field strength that we've coupled to the zero form symmetry. Okay, so given this anomalous variation, if we just did a background gauge transformation, we would find that the action transforms in a way that depends on the background gauge fields and the gauge fields of the actual gauge symmetry. And we can just recognize that actually this field strength of the U1 gauge symmetry, as it appears here, is actually the current for the magnetic one-form symmetry. So we can just rewrite this as a sort of product of the field strength of the background gauge field and the conserved symmetry current of the magnetic one-form symmetry. And so this is the anomalous variation of the action under a gauge transformation of the background gauge fields coupled to our global symmetry. But since we've gauged the magnetic one-form symmetry as well, we could imagine if we do a special choice of a background gauge field transformation for the gauge field that couples to the one-form symmetry, we can choose that to tidy up this anomalous variation. In particular, if we choose the gauge transformation for the background gauge field coupled with magnetic one-form symmetry, it can have whatever transformation we want on its own, plus a piece which is chosen specially so that it will cancel off the anomalous variation from the zero form symmetry. So there's a sense in which this good higher form symmetry is clearing up the anomalous variation of the action coming from the bad zero form symmetry. And that's a sense in which now these two symmetries mix. In other words, the one of the symmetries is not a good symmetry on its own, but can be promoted to a good symmetry in the presence of the one form symmetry. So at this point, I'm going to introduce a character, which actually, do any of you in the audience, this is a test of whether you have children between the ages of 3 and 9. Anyone recognize unicorns? Okay, all right, very good. Yes. Okay, so for those of you whose lives have been dominated by Bluey over the last few years, there's an extremely annoying character in this kids show. So we're in a golden age of quantum field theory. We're also in a golden age of children's television. There's a very annoying character, though, in this kids' TV show called Bluey, called Unicorse, whose slogan is, "And why should I care?" And surely you're all at the point, we've just talked about this very complicated H'tooth anomaly that causes this one-form symmetry to mix with zero-form symmetry, and you no doubt are personifying Unicorse and politely wondering to yourself, and why should I care? So why should you care? So it's typically the case, as I've already said, when you have these higher form symmetries, it's typically true that the symmetries themselves are emergent. And we've learned in this example, the one form symmetry is good on its own, right? But the zero form flavor symmetry is not. It's only a good symmetry when the one form symmetry is around to clear it up. Unless we expect that if these symmetries both emerge as a function of scale, the good symmetry has to emerge before, as a function of scale, the bad symmetry. It would be inconsistent to have a theory where there's only the bad symmetry for some regime. That would be, again, in the spirit of H'tooth anomalies. If it was a true anomaly, we'd be overcounting the path integral. And so it must be the case that the one form symmetry emerges at or above the scale of the zero form symmetry. And this is plausibly powerful, right? Because if you're a particle theorist, regardless of what theory you're studying, if your EFT has a higher group symmetry, then this actually tells you something very general about the properties of its many possible EV completions. Right, and that seems like something very powerful and interesting to us as field theorists. And you can test it out in various ways. So in the original paper on higher group symmetries in 2018, they said, well, let's see how it plays out in this story. So for example, if you UV completed the U1 gauge theory into an SU2, you find that both the one form symmetry and the zero form symmetry are emergent symmetries, and they satisfy this emergence criteria. So for example, if you imagine that the U1 gauge theory was UV completed in an SU2, you could fit the 4 fermions into 2 SU2 doublets. The one form symmetry is emergent because, of course, there are H'tooth polycov monopoles from this breaking. And so those monopoles, they're dynamical at some scale, and that explicitly breaks the magnetic one form symmetry. Below the scale of the monopoles, the magnetic one form symmetry is emergent. And the zero form flavor symmetry we picked out is also emergent because the generator doesn't commute with the generators of SU2. And so it's also an emergent symmetry below the scale of breaking of SU2. So this is an example where, in some sense, there's one scale where both the one form symmetry and the zero form symmetry emerge. It's effectively speaking 1 over the radius of the monopoles, or the mass of the W boson. And so, below that scale, we get this EFT with this higher group symmetry. Above the scale, the symmetries disappear, but indeed they satisfy in a sort of trivial way this emergence criteria. The 2 symmetries show up at the same scale. And the claim is that this is a very powerful constraint. And in fact, regardless of how you complete the EFT, this should always be true. Now, I'll tell you at the end of the talk, this is always true, but for reasons that are very different from the story that was originally told. So I'll explain that by the end of the talk, which hopefully in a way that turns out to be interesting. But, yeah.
Can you explain again the argument for why the one for symmetry emerged before the zero for symmetry?
Oh, so good. You imagine these symmetries emerging as a function of scale. If the zero form symmetry emerged at a higher scale, there would be an energy regime, again, turning on the background gauge fields, in which you simply had an anomalous theory, right? It is only when the one form symmetry appears that the anomalous variation can be canceled by the appropriately chosen variation of the one form symmetry. And so, it's now, you could ask the question, in the same way that we say, it's not that you're not allowed to have anomalous gauge theories, it's just that anomalous gauge theories are effective field theories with a bounded regime of validity. That is also true here. So indeed, the appropriate argument is really that there can be, in some sense, a bounded regime in which the zero form symmetry emerges before the one form symmetry has to emerge. And they didn't treat this in the original papers. They just put a tilde inequality. I think if you try to frame it precisely, you would say, in exact analogy with anomalous gauge theories as an EFT, you could have an anomalous zero form symmetry over a bounded regime. But actually, as I'll explain to you, this was not in the original papers. I haven't spoken to the authors themselves about this, but so this turns out to be trivially satisfied, basically because the ingredients required for the one form symmetry to be emergent, plus the fact that there is a H'tooth anomaly, guarantees that the zero form symmetry is never a good symmetry above the scale of emergence of the one form symmetry. So I'll get to that at the end of the talk. And so that in some sense trivializes this relative to the original paper, but it points us in a new interesting direction. but I'll tell you that in a few minutes.
So, but to cancel the anomaly, the B field that you introduce need to be another new dynamical degree of freedom.
Well, it's the normal logic of HEP anomalies, right? Both the background gauge field coupled to the zero form flavor symmetry and the background gauge field coupled to the one form symmetry are just, fictitious. We are imagining if they were actual symmetries, gauge symmetries, which they are not, but nonetheless, they could be extremely weakly coupled gauge symmetries, in which case certain consistency conditions would follow.
So, but if they are not gauged, why do you want them to?
Well,
But you
it's
want
the
to
same,
do
it's the same logic that H'tooft used for the original arguments of H'tooft anomaly matching, is that you couldn't tell the difference between an extremely weakly gauged gauge symmetry and a global symmetry. And therefore, the theory should obey the consistency conditions implied by even a weakly gauged gauge symmetry.
Yeah, but the consistency conditions were simply that the anomaly at
Right.
high scale and low scale. were
And in that case, there were additional dynamical degrees of freedom there to cancel the anomaly were fermions, right? Spectator fermions, which then, you carried through the threshold of whatever interesting dynamics happen. And that's how you argue for anomaly matching. The two form field coupled to the zero form symmetry current is just the same. It's like the spectator fermions. Now it's just the spectator two form gauge field. And it's just that the appropriate ingredient now for a higher form global symmetry as opposed to an ordinary symmetry. So anyway, to bring you back to Unicourse, as a particle theorist, why should you care? This seems to be very powerful. Indeed, we'll see that it's satisfied in a different way than the original authors proposed, but keeping this in mind, I think does point us into interesting new directions. Okay, something very similar happens if the anomaly is actually not a H'tooft anomaly, but a genuine ABJ anomaly. I'm going to say this very concisely, and so I apologize for suppressing the details. But it's also what often happens is you can often end up in a situation where you have a zero form global symmetry, which has an ABJ anomaly. And although one thing that happens in that case is the good, say the abelian continuous global symmetry is often broken down to a discrete subgroup as a normal symmetry. But there's also a bit more symmetry that's left behind, which has some unusual properties. The basic idea is that the symmetry defect operators that describe the full symmetry, in a case where you have a global symmetry that's broken by an anomaly, instead of being symmetry defect operators that reproduce a group structure, they're symmetry defect operators that reproduce a fusion algebra, in the sense that if I bring two of them together, instead of necessarily getting another symmetry defect operator corresponding to the group product, I can instead get a linear combination of symmetry defect operators with relative coefficients, which describes some sort of fusion algebra. And of course, when this is true, you're no longer guaranteed that inverses exist for every one of these elements. So the symmetry, therefore, is non-invertible. The sharp example that we're going to make use of in today's talk is if you just think about a 4D U1 gauge theory that has a U1 axial symmetry with an ABJ anomaly. Of course, the axial anomaly tells us that the axial symmetry current is no longer conserved. That means the symmetry defect operator is no longer topological. Of course, decades ago, Jakif told us how to fix this. We could simply define an improved current, which is conserved, and therefore the symmetry defect operator is topological. However, the problem with Jakif's picture is the improved current was no longer invariant under large gauge transformations. And the innovation over the last few years is that one can clean up the gauge non-invariance by defining the topological field theory that lives on the symmetry defect operator. And the addition of this extra ingredient gives you now a notion of symmetry defect operators with improved currents that are conserved and gauge invariant. And the price that you pay is that the symmetry defect operators no longer respect a group structure, but instead respect a fusion algebra, and they're not necessarily inverses. For our purposes, the thing that I want you to pay attention to is when this happens, when I bring together a symmetry defect operator for this anomalous zero form symmetry with what should be its inverse, instead of getting the identity, I get something that's actually proportional to the magnetic one form symmetry of this U1 gauge theory. And so just like for the higher group structure, where we saw that the magnetic one form symmetry entered to clean up the anomalous variation of the zero form symmetry, when there's a true anomaly of the zero form symmetry, an actual ABJ anomaly, something very similar happens. And for our purposes, that means there's a similar set of statements about emergence. Okay, that the one form symmetry should emerge at or above the scale of the zero form symmetry, and that is something with interesting phenomenological consequences. Okay. So at that point, that's the not so lightning introduction to generalized symmetries. Hopefully, at least you have a sense, if you haven't thought about this before, what the ingredients are and how they might be relevant to us. And so for the rest of the talk, I just want to give you two examples to answer unicourse, which is why these might actually tell us some new things about particle physics. And again, I want to be careful here and say there have been many applications of generalized symmetries to particle physics over the last few years. I would say many of them fall in the category of using new words to describe old things. And so the examples I'm going to give you today, while they might not be as outrageously awesome sounding as those other claims, I hope that they are a bit more conservative in the sense that they really do use the language of generalized symmetries to teach us something new that we might not have recognized before. Okay, so the second part of my talk is now about high quality axions and higher form symmetries. This is work done with Marius, so I'm going to actually state the results somewhat concisely because you may well have heard the story from Marius already. The motivation for this is one that as a particle physicist has been with us for a very long time. So I think probably here it's safe not to spend too much time introducing and motivating axions themselves, but to the extent that we think that there might be a problem with CP violation in the strong interactions, which is not currently observed. We could explain it by introducing a Goldstone boson of an anomalous symmetry, which cancels the CP violation of QCD at its minimum. And so the familiar way that we do this is we imagine that there's a U1 global symmetry, a Hedgeroth symmetry that's spontaneously broken. The Goldstone, of course, is the axion. We imagine that the only explicit breaking of this zero form symmetry is from QCD via the anomaly. And so then it turns out that, of course, given this potential, the vacuum expectation value of the axion neutralizes the theta term of QCD at the minimum. So we solve strong CP with the axion. Of course, we've known for a long time that the story isn't quite as simple. The story works beautifully if we posit that the only breaking of this zero form symmetry is via QCD. Any other explicit violation of this Hedgeroth symmetry in the ultraviolet by irrelevant operators spoil the solution. Basically, if I have irrelevant operators which explicitly violate the U1 symmetry, for example, they carry some net charge and some relative phase, then they give a contribution to the axion potential, which shifts its minimum away from the value that neutralizes the theta term. And it turns out because we need to cancel theta to very high precision, even incredibly small irrelevant operators are dangerous. So this is an example, unlike higher form symmetries, which are very good symmetries if they emerge in infrared, a Hedgeroth symmetry, even if it's broken by incredibly high dimensional operators, can still be compromised. And of course, much work has been done pointing out that this is not just a naive effective field theory concern, but actually genuinely appears to be a problem in UV completions. So of course, there's a long history of model building solutions designed to improve the quality of this Hedgeroth symmetry. But inevitably, they complicate the simplicity of the axion solution to the strong CP problem. There is, however, a possible avenue for obtaining the axion, which seems compelling from the perspective of the quality problem, which is that axions don't just have to be Goldstone bosons of a spontaneously broken Hedgeroth symmetry. They can also rise from the compactification of higher dimensional theories. If there are gauge fields living in the higher dimensional theories, when we compactify them and come up with a four-dimensional effective theory, that can also give us axions. And because they're not coming necessarily from some original zero form symmetry, they can have much better properties. So of course, this has been very long known in string theory, but for the purpose of today's talk, since we're oriented towards particle physics, the essential physics can be understood just using field theory and just thinking about a U1 gauge theory living in 5 dimensions, where we compactify one of those dimensions on a circle of fixed radius to get down to a 4-dimensional theory. So the way to think about this is you could just start with the gauge field in 5 dimensions. We want this to be a stand-in for the axion of QCD. So we also have to imagine that there's a QCD sector or some Yang-Mills sector, and there needs to be an anomaly term in 5 dimensions, which will boil down to the axion coupling to GG dual in 4 dimensions. So now, of course, we compactify this 5D theory, we compactify 1 dimension on a circle. Of course, that can now decompose in some appropriately chosen frame, the 5-dimensional U1 gauge field into a 4-dimensional vector and a scalar. And the interesting degree of freedom from the 4-dimensional perspective is the integral of that 5th component on the circle. So this gives us a periodic scalar in 4 dimensions, which we can identify with the axion. And given the simple toy model in 5D, it gives us an effective theory in 4 dimensions, where these are just the 0 modes, where there's an axion-like degree of freedom. The axion decay constant depends on the radius of rectification and the 5D gauge coupling, and it couples to GD dual, just like you would have expected an axion to do. Okay, so this is a good candidate now for the axion coming from the fifth component of a gauge field 5 dimension. And the reason why this seems exciting, I've just decided to pull some text from one of the original papers. This was not talking about, of course, the QC axion, but also using the same ideas for inflation. The enthusiasm for getting the axion from a high dimensional gauge field is that it cannot have a local potential due to the high dimensional gauge invariance. A shift symmetry protects it, similar to what happens to a 4-dimensional Goldstone boson. And they emphasize here that locality in the extra space is the key feature. UV physics like virtual black holes cannot spoil the gauge invariance and do not introduce a local potential for the fifth component, while non-local effects are exponentially suppressed by the size of the extra dimension. So this is, in some sense, a recipe for coming up with axions that have extremely high qualities. The quality is coming, at least as originally stated, from gauge invariance in the extra dimension. But if you think about this for a bit, this can't be the whole understanding of why this is good as an axion. Among other things, right? As we're told as children, gauge symmetry is not a symmetry, but a redundancy of description. Right? It would be satisfying to have a global symmetry depiction of what's happening in the story. Extra dimensional gauge invariance doesn't actually protect against all possible contributions to the axion potential. So for example, in our 5D gauge theory, gauge invariance doesn't prevent us from writing a Stuckelberg mass for the 5D UN gauge field, and that would necessarily give complications for the 4-dimensional picture. So gauge invariance doesn't protect against all possible contributions. And then finally, although there's this expectation that there are non-local effects that should be exponentially suppressed, the question you presumably have, if you don't want to work out the details, is how can you systematically account for all of the non-local effects? What effects contribute? What are their parametric size? And how do they relate to our expectations about axion quality from gravity? Okay. And so, as you've no doubt imagined, there is a global symmetry that explains what's going on here. It's just the one-form symmetry of the 5-dimensional vector field. So here's my non-children's television meme. Is that rather than invoking in this extra-dimensional axion story, a 4D axion that's protected by 5-dimensional gauge symmetry, hopefully I can persuade you that it's much more productive to think about this as actually being due to the one-form symmetry of the 5-dimensional theory. And I think although once you understand generalized symmetries and think about extra-dimensional axions, it's sort of obvious that this has to be true. To my knowledge, the first time that this was said explicitly anywhere was in Matt Reese's Tazi lectures. Matt himself has also pursued aspects of this picture that are slightly orthogonal to what I'll tell you about next. Okay, so the idea here is just that what's actually making a good axion is that this, if you think about the 5-dimensional gauge theory that will descend down to give you the axion in 4 dimensions, the free UN gauge theory, it has an electric one-form symmetry, as we described. Its magnetic symmetry is not a one-form symmetry, but a 2-form symmetry, because in 5 dimensions, the dual field strength is a 3 tensor object, 3 index tensor object. And so these are 2 higher form symmetries of the 5D UN gauge theory. The shift symmetry that we think of as the axion shift symmetry in 4 dimensions lives in the electric one-form symmetry. The fact that these symmetries, when emergent, are very well protected against UV breaking means that that is, at the end of the day, why the axion is protected from dangerous UV corrections. And to see what the relation should be between these ingredients, it's just helpful to think of the decomposition of the higher form symmetries in 5 dimensions relative to the symmetries of the 4-dimensional theory. So the 5-dimensional theory, there's the electric one-form symmetry and the magnetic 2-form symmetry. When you compactify and work out the effective theory, the electric one-form symmetry in 5D decomposes to an electric one-form symmetry for the surviving 4-dimensional vector, and also the 0-form shift symmetry that we recognize as the axion shift symmetry. So the axion shift symmetry just lives in the electric one-form symmetry. Potentially even more interesting, of course, we've said that periodic scalars also have a 2-form symmetry, but we can see very clearly in this picture the 2-form symmetry actually comes from the magnetic 2-form symmetry in 5 dimensions. So decomposing that symmetry, you get the scalar 2-form symmetry and the magnetic 1-form symmetry of the 4D vector. And now you can go about systematically understanding, since we're talking about higher form symmetries, what effects can break them and what the size of that breaking is in terms of contributions to the axion. So again, the basic idea is for the free UN gauge theory in 5 dimensions, there's an electric one-form symmetry, which is conserved via the equations of motion, the magnetic two-form symmetry, which is conserved by the Bianchi identity, and the shift symmetry now lives in the electric one-form symmetry. So we can now just go about, once we know what the symmetry is that's protecting the axion in 5 dimensions, we can go about and systematically enumerate all of the possible effects that can break the global symmetry, and we can estimate or compute their sizes to validate this idea that the axion is exponentially well protected against UV physics. In the interest of time, although I have slides for each one of these effects, I think it's probably best just to briefly tell you about them. I'm happy to discuss in detail after the talk, because I want to take you also from this example to one more example of higher form symmetries in particle physics. But the basic idea is there are in some sense 3 ways that we can break the electric one-form symmetry to give the axion a potential. There's also a 4th thing we can do, which is actually, the electric one-form symmetry is a global symmetry, and we can imagine gauging it. Now, that makes the symmetry extremely good, but it has the consequence that the axion is actually eaten in the gauging of the symmetry. And so in some sense, that removes the axion as an interesting degree of freedom for solving the struct CP problem. So in some sense, that means there's 4 effects, 3 of them are breaking, and 1 of them is gauging. So the 4 effects are as follows. Of course, as we know, electric one-form symmetries can be broken by electrically charged matter. So we could have electrically charged fields in 5 dimensions. They preserve a discrete subgroup of the original symmetry, the one-form symmetry. And then they give us a potential when we boil it down to 4 dimensions. They give a periodic potential for the axion, which indeed is exponentially small in the size of the extra dimension as claimed. So this is a relatively straightforward effect to compute, and is one that, of course, has been known for a long time. But now we can understand it very simply as being due to the fact that electrically charged objects explicitly break electric one-form symmetries. Another effect that we can introduce that breaks the electric one-form symmetry is we can actually gauge the magnetic two-form symmetry. And this has the effect of breaking the electric one-form symmetry because now there's an additional term that appears, so no longer the current is no longer conserved. This preserves a remnant symmetry, which depends on the coefficient of the gauging. And when you boil it down to 4 dimensions, what you see is this effectively is what we would call a monodromy mass of the axion. So the axion picks up a mass depending on the gauging of the magnetic two-form symmetry. There's a 3rd form of breaking, which is breaking by an anomaly. Again, this is already what QCD does for the ordinary axion. And so, of course, if we have the anomaly term that couples the abelian gauge field to, say, Bolk-Yang-Mills gauge fields, unsurprisingly, there's now a density that appears on the right-hand side. This breaks the symmetry down to a discrete subgroup. And of course, instanton effects on the right-hand side give the axion a potential. So those are the, but I want to emphasize, although this effect has to be here for QCD, if there are additional gauge fields that couple the anomaly terms in the 5D theory, they will also give contributions to the potential of the axion. And the final effect to emphasize is we can also go in the opposite direction. We can make the electric one-form symmetry very good by gauging it. But what happens there is actually that the degree of freedom that we want to be the axion actually gets eaten. And so although we have a very good electric one-form symmetry, it's now a local one-form symmetry. The axion is now a longitudinal mode of a massive vector in 4 dimensions. And so it's no longer a useful light degree of freedom for our purposes. So I leave the details of all of these forms of explicit breaking and their parametric sizes in some slides I'm happy to discuss afterwards. But I just want to leave you with this idea that recognizing that what's happening here is that there's a higher form symmetry protecting the axion gives us a very systematic way of understanding the effects that can break it. Of course, once you've also been able to parameterize all the possible effects that can break the one-form symmetry, for example, through charged matter or anomaly terms, then you can ask, what is the natural size that you expect these breaking effects to be in a theory with gravity? And here, of course, we can now make connection to the various forms of weak gravity conjecture, which relate bounds on the scale of charged particles or charged extended objects to the scale of quantum gravity. And the answer is when you apply the appropriate version of the weak gravity conjecture, either the 5-dimensional electric weak gravity conjecture, magnetic weak gravity conjecture, or even higher form versions of the weak gravity conjecture in 5 dimensions. They, of course, tell you that you cannot arbitrarily couple charged particles, for example, in the theory, and so that there are effects that will break this shift symmetry of the axion, but they are necessarily exponentially small compared to your 4-dimensional expectations. So when you try to estimate the size of gravitational effects through the breaking of the one-form symmetry, indeed, your less than is these higher dimensional axions, as expected, have exceptionally high quality. So at this point, Unicourse comes back. Okay, so you may again be wondering, why should I care? So back in 2003, we already had an idea that axions coming from extra dimensions have an exceptionally high quality. Maybe the explanation we used for it wasn't completely hermetic, but it nonetheless had the right sense of what was going on. So what have we gotten apart from a nice organizing principle of reimagining this in the language of generalized symmetries? And I think the answer is we've learned that there is a very interesting system whose phenomenology is almost entirely unexplored. And the reason we're pointing to that system is actually from the analogy of the generalized symmetries. So there's, I think, a folklore now that's taking hold in the field where you have a trade-off. Either you have a four-dimensional axion, which comes from a Peche-Quinn symmetry, and that symmetry could be broken after inflation, in which case you have a post-inflationary axion scenario. And that's a very interesting scenario because it's highly predictive. Axion strings that are produced, then those string networks collapse, and they have a very predictive relation between the mass of the axion and the abundance of the axion in the present day. So this is a very sharp target for axion searches. But the trade-off seems to be if you want to improve the quality of the axion, and so you have it come from extra dimensions, there are no axion strings from the extra dimensional axion, and so there's no post-inflationary axion scenario. And of course, there are some exceptions to this rule. Shobi has done some nice work pointing out these exceptions, but they generally have a tension between having interesting post-inflationary axion cosmology or having a high-quality axion. But I've already given you an example. If we think of the axion as coming from 5 dimensions, there can be magnetic monopole strings in the 5-dimensional theory. And those magnetic monopole strings, their world sheets are charged under the magnetic two-form symmetry in 5 dimensions. We know the axion in 4 dimensions has a two-form symmetry. The charge objects are the axion strings. And so that immediately suggests to you that you should think of the magnetic monopole strings in 5 dimensions as being the progenitors of axion in 4 dimensions when you have extra dimensional axion. And this turns out to be a really productive direction. So we're still exploring all of it, but just to give you the basic idea, if, for example, your 5-dimensional U1, just imagine it comes from the breaking of SU2 down to U1, then in the 5D theory, there are Hatuf polycog monopole strings. At the core of those strings, SU2 is restored. If you imagined in the early universe to inflate above the radius of impactification, you make these strings as standard topological defects in the early universe. And then as you cool down into the 4-dimensional effective theory, 2 things happen. Some of the strings wrap the extra dimension, and those turn out to be interesting stabilized objects. Some of them are just point-like monopoles. Some of them are actually static ring solutions, which are not solutions of the 4D theory, but are instead 4-dimensional rings that are sustained by their momentum in the 5th dimension. There are also Hatuf polycog monopole strings which don't wrap the extra dimension. Those are not solutions to the 4-dimensional theory, and they're not stabilized, so they should decay and make axion. And so there's a picture here in which there's a post-inflationary axion scenario for extra dimensional axions, which is almost entirely unexplored and has many, many rich phenomenological consequences. So this is an example of a direction in which we're pointed by thinking about this in the language of generalized symmetries. Okay. So the exploration of that is underway, especially with this audience. I'd be delighted to talk to many of you afterwards. I know lots of you have thought about both inflation and extra dimensions and the fate of solid ionic objects under compactification, and they all seem to play a role in that phenomenology. But I want to end with one more example, which I think is another example of how thinking about generalized symmetries in particle physics have reminded us of something that we missed. In this case, it's something that we appear to miss from the 1980s. And in this example, I'm also going to come back to the original question of how should we think about the emergence conjectures that arise when we have mixing in the higher group structure. Okay. So let's come back to the standard model. And so, as I already said, generalized symmetries are everywhere in particle physics, and it turns out the standard model has many generalized symmetries. One of the sets of generalized symmetries that it has is apparent if you think about, as we're all taught from an early age, we say, here's the field content of the standard model. If we turn off the Yukawa couplings, there's a large global symmetry. It's a U3 to the 5th symmetry, where we take the 3 generations of each type of fermion and rotate them into each other. And it turns out that actually this flavor symmetry, each one of these U3 factors forms a 2-group structure with the magnetic 1-form symmetry of hypercharge. So of course, if I give you the standard model and no monopoles, the standard model has a magnetic 1-form symmetry. But it turns out that there are Hooft anomalies between the flavor symmetries of the standard model and that one form symmetry and hypercharge, so there's a two group structure. And so it turns out each one of these U3 factors, here I've just written the U1 parts of the U3s, but up to scalings, it's also true for the SU3 parts. Each one of them has a 't Hooft anomaly with hypercharge with a non-zero anomaly coefficient. All right. But of course, if you inspect these anomaly coefficients, you can see if I make combinations, I can define flavor symmetries that are linear combinations of the underlying flavor symmetry in the standard model. And those appropriately chosen linear combinations could be anomaly free. For example, if I combine D and L, the combination of U1D and U1L doesn't have a 't Hooft anomaly with hypercharge. So if the standard model, if the flavor symmetries participate in the two group, we've already said if we have a higher group structure, this emergence conjecture says the good symmetry, which is the one form symmetry of hypercharge, always has to emerge at or above the scale of the bad symmetry, which is the flavor symmetry. So one consequence of that is, of course, we know one place where the magnetic one form symmetry is emergent is if the standard model unifies into a gauge group whose breaking produces monopoles, right? The one form symmetry is emergent below the scale of those monopoles. And so this higher group structure, as pointed out by Clay and Seth in 2022, this seems to have some interesting implications. It tells you that since the one form symmetry only becomes good below the scale of unification, individual flavor symmetries that have a 't Hooft anomaly with hypercharge cannot be good flavor symmetries of the unified theory. Unsurprisingly, though, linear combinations of them can be. And so if you ask what linear combinations are anomaly free, you reproduce the list of possible consistent unified embeddings of the standard model fermions. Now, that's an amusing fact. Of course, we already knew how to enumerate all of the embeddings of standard model fermions, so it doesn't tell us something new, but it is plausibly an interesting consequence of this higher group structure. Okay. What I want to tell you today is that may all be true, but actually there is a lot more going on in the generalized symmetry structure of the standard model. And the same story tells us, I think, some interesting and deeper things that have been missed the first few times around. Okay. So I think it's fair to say that Seth and Clay missed what is, I think, the most interesting effect of the situation, which is that, as we've known for a long time, if you have monopoles, they can catalyze violation of global symmetries via the Callan-Rubikoff effect. Now, there's two parts to the Callan-Rubikoff story. You've probably heard about one of them a lot lately. So the two parts are, one, that monopoles catalyze violation of global symmetries, and two, that of the symmetries that are preserved, it's often the case that the outgoing states don't appear to be in the Hilbert space defined by the ingoing states. And so the question is, what are the outgoing states? I'm not interested for our purposes today. We're not interested in that second question. What we're interested in is the first question, which is what global symmetries are just violated in scattering off of monopoles. And the version of the story that's most familiar to people is monopole catalyzed proton decay. So the story that was told by Callan-Rubikoff in the 80s, the intuition is if you have, there can be, for example, fermions carrying, for example, baryon number. As they scatter off of the monopole, they can penetrate to the core of the monopole. And if it's a gut monopole, then there are X and Y gauge bosons at the core of the monopole. Those mediate baryon number violation. And so that is the sense in which scattering of monopoles can, for example, induce photonics decay. It turns out you can ask more broadly, what are the global symmetries that are violated in scattering off of monopoles? And it turns out that essentially by definition, if the ordinary zero form symmetry, the flavor symmetry, participates in the two group, okay, with the magnetic one form symmetry that's broken by the monopole, then those are the symmetries that are broken by scattering off the monopole. So this was first said precisely in a nice paper by David Tong and Zohar and collaborators, but actually it rests on some beautiful statements about the violation of anomalous symmetries at boundaries, including work by Yifan Wang. And so basically the answer is if you have a zero form flavor symmetry and it's part of a two group, and the one form symmetry of the two group is broken by a monopole, the global symmetry will be broken if you scatter off the monopoles. And so this actually is a more satisfying answer to the emergence conjecture, right? It tells you if the one form symmetry is emergent because there are monopoles of Monodrome scale, the existence of monopoles plus the 't Hooft anomaly tells you the zero form symmetry is always violated. Okay, so the pessimistic conclusion is there will never be interesting phenomenological consequences of emergence because it is sort of tautologically satisfied. Okay. So that's the pessimism. But I want to emphasize there's some optimism, which is that recognizing that what's actually happening in these examples is it's reminding us of the existence of monopole catalysis. That can actually point us to think about some things that we didn't think about necessarily in the 1980s. So I just want to give you one example because I know I'm going over time. One thing I want to emphasize is actually the higher group structure of the standard model is even richer than just these two group symmetries that arise from the fifth anomalies. There are also, of course, famously the electroweak anomalies of standard model flavor symmetries with both hypercharge and the SE2 left gauge group of the standard model. And as I've already mentioned, of course, if you have a global symmetry with a true ABJ anomaly, then the global symmetry becomes non-invertible and it's subject to analogous statements about the emergence of the symmetry. Okay. And so I just want to focus your attention on one example of a physical consequence that follows from this. So if you think about baryon number in the standard model, it of course has an ABJ anomaly with hypercharge, so it's a non-invertible symmetry. And so the same emergence criteria tells us baryon number should be broken above the scale of U1 hypercharged monopoles. Now, we already knew that the story was true for SU5 and SO10. This is just Kalin-Rubikov, right? It tells you that baryon number is violated by scattering off of those gut monopoles. And the reason we said that that was true was because in the core of the monopoles, there are baryon number violating interactions mediated by the gauge bosons. But the same conclusion should also hold in unified theories that preserve baryon number, where the gauge bosons don't mediate baryon number violation, right? Because this logic is ironclad. Okay, these give us monopoles, so it should be the case that these also violate baryon number, even though there's no gauge bosons in the core of the monopole that are mediating baryon number violating interaction. So that's interesting. It turns out this was understood actually for Padi Salam by Sen in a very little known paper in 1984, where Sen indeed observed that although, so Padi Salam is an amusing unified theory, although baryons and leptons are unified in same multiplets, exchange of the vector bosons doesn't violate baryon number, so it's an accidental symmetry. But because there is the electroweak anomaly of baryon number, there are scattering processes off of Padi Salam monopoles. What's very interesting about them is the leading contribution is actually not baryon number violation by a single unit, but in fact baryon number violation by 3 units, essentially because the scattering, the condensates need to see the presence of altered generations in the standard model. So this was sort of waved at by Frank in 1982, but really Sen worked it out in detail in 1984. So this is an example of an effect that was known, but we're reminded of it, and it's very interesting because it tells you there are monopole-mediated baryon number violating processes where delta B is 3. It also tells us, of course, that the same thing should be true in trinification. Trinification is even friendlier to proton stability because baryons and leptons are in separate multiplets. So baryon number is very clearly a good symmetry to theory. It turns out trinification has very fun monopoles. So they carry 3 quanta of magnetic charge. Those are lowest charge objects, no color magnetic charge. But because of the electroweak anomaly, you can also prove to yourself, using analogous logic to Sen, that there is baryon number violation in scattering off of these monopoles. As far as I know, this has never been mentioned. So we think of trinification as being a completely baryon number preserving theory, but it actually, in scattering off of its monopoles, violates baryon number by 3 units. I'm on an ongoing quest to see if this was known to somebody, but Howard Georgi says they didn't know it. So if Georgi says they didn't know it, I'm see if it wasn't known. And you know, coming back to unicourse, okay, why should I care? There's monopoles violating baryon number by 3 units in trinification. Okay, well, it's telling us something that maybe we missed in the 1980s, but these are actually very interesting. Both of these are very interesting sets of monopoles, and the baryon number violating processes they mediate are very different, of course, from ordinary baryon number violation by monopoles. So there are some fun properties of these monopoles. For example, the trinification monopoles are not spherically symmetric, so there's interesting subtleties for how you study fermion scattering off of them. Also, because depending on how unified trinification is, the scales can be much lighter. It's plausible that these monopoles, you know, could be much lighter than 10 to the 16 GeV and much less constrained in our universe. And although we know we have very strong bounds on monopoles that violate baryon number by 1 unit, for example, by the way in which they change luminosities of astrophysical objects, to my knowledge, there has not been a study of what the astrophysical observables are if you have monopoles that violate baryon number by delta B is equal to 3 living inside of astrophysical objects. And so there's just really interesting questions about the astrophysical signatures of these monopoles that I don't think have been explored. Certainly not for trinification, because until this year, I don't think we knew that this happened. Okay. Good. So that's hopefully Unicourse convinces you that this is something that's worth caring about. And this was a conclusion that really is given to you by approaching this problem from the language of generalized symmetries. Okay, I know I've gone over as is my wont, so let me just briefly wrap up. So as I hope I've conveyed, generalized symmetries are abundant in the standard model and theories we care about the physics beyond the standard model. What I think is interesting for us as particle physicists is not so much enumerating the exact symmetries, but is understanding what are the approximate selection rules that arise from their breaking. We're very much in the early days of doing that, so there's currently no spurion analysis for explicit breaking of higher form symmetries or non-invertible symmetries, and simply doing that itself would be very interesting. But also thinking carefully about what new lessons they tell us, I think there's a lot to be gained. So I've tried to give you two examples. One is to clarify this understanding of extra dimensional axions, with the phenomenological conclusion being there's a really interesting extra dimensional post-inflationary axion scenario we've never studied, and now we can. And then I've taken us back to the physics of monopoles coming from unified theories. We've, in some sense, discovered baryon number violation in unified theory that we didn't think had baryon number violation. And these delta B is equal to 3 processes are astrophysically very interesting, and I think would be a lot of fun to study further. So this is small progress, right? I'm not telling you I've solved the hierarchy problem with generalized symmetries. I think that probably is a remote possibility. But I think if we really invest in understanding generalized symmetries and carefully and soberly think about how they play out in the physics that we care about, we can start to use them to discover something. Thanks very much.
Questions for Nathaniel?
Do you have any sense for like the mass of these delta P equals 3 monopoles? Like what's constrained
they're
by
always-
their
they're-
protection?
They're always a scale of unification, right?
Yeah.
So for, of course, if you're saying Patti-Salam or trinification is a true unified theory, then those scales are just set by when the couplings are going to cross. But of course, one of the things about trinification that's fun is if you're interested more in the trin than the fication part, right? So you relax the Z3 that relates to gauge couplings, then the scale of trinification breaking can be as low as tens of TeV. And so in principle, then that tells you here's a very interesting theory where there are just polycount monopoles as low as tens of TeV, which violate baryon number by delta B is equal to 3. The lighter the monopoles, the less constraining the Parker bound is. And so that means their cosmological abundance, astrophysical abundance can be more interesting. And then, yeah, this question of whether any astrophysical bounds are relevant for them from baryon number violation, I think as far as I know, is not been looked at at all. And it is interesting because, of course, if you're violating baryon number by 3 units, there's now a kinematic threshold to baryon number violating processes. So there should be signals, but they are going to necessarily be weaker than the delta B is equal to 1.
If there are no more questions, we can thank Nathaniel again, and those who are interested for more